Hello, my name is Luke Wilson, and this is my Engineering Physics 2CM4 design project. The agenda for this presentation is to look at the problem that I came up with this project, look at the approach that I took to solving this problem, seeing how I integrated this approach into mathematical models, looking at the results outputted by these mathematical models, and then reflecting on these results to see if they make sense. When a space capsule enters the atmosphere of a planet, the friction produced by its movement against the atmosphere creates a lot of heat. So thermal protection systems are used to protect spacecraft from heating experienced during atmospheric entry. Now, there have been a lot of different materials used to protect against this heat in the past. However, pica, which is phenolic impregnated carbon-based ablator, is a more recently developed material used for thermal protection systems. So for my project, I wanted to optimize the thickness of a single pica tile used to construct an entire heat shield. Now, there were some constraints that came along with this solution. So first, the inner surface temperature of the pica tile must remain under 176 degrees Celsius for a heating time of 90 seconds. So that means the outer surface of the tile would be heated for 90 seconds, and it can't go above this temperature limit because that is the failure temperature of the aluminum airframe. Now, when calculating the mass, I considered that my space capsule would have a diameter of 4.5 meters, which means it would have a total area of 15.9 meters squared. So in the end, I divided the total area of the heat shield by the area of the tile to find the total number of tiles needed to construct this heat shield. And then I multiplied the number of tiles by the mass of each tile, which was calculated by multiplying the volume of each tile by the density to find the total mass. And also, the side lengths of the square tiles were equal to 5 times the thickness of each tile. Okay, so for my approach, and just to give some background, in the bottom right figure, there's a picture from the work that Allen and Eggers did in the 1960s at the NASA Ames laboratory, where they found that increasing drag reduces the heat energy incident on the surface of a ballistic because this shock wave is produced, which deflects some of the heat energy. However, the heating loads that we're dealing with are still significant enough where we need a thermal protection system. And that's where the pica material comes into play because it is a very good defense against this heat energy. And there are some figures in the top right that kind of illustrate how pica kind of absorbs and re-radiates heat and insulates the inner surface of the tile. Okay, so then we also had to integrate the heat flow equations into my solution. So I have the equation for heat flow, and then I combined the convective and radiative heat transfer equations to come up with an equation for the heating load that I used in my mathematical models. Okay, so next, FlexPDE and Spider are two of the softwares that I use to come up with my mathematical models. So in FlexPDE, I modeled a 3D tile, added the heating load corresponding to the equation in the previous slide to one side, and ran the simulation for a time of 90 seconds, and then outputted the average surface temperature of the inner surface. And then in Spider, I iterated through different thicknesses, and then I found the ideal thickness, and then I calculated the final average temperature on the inside surface and the mass of the heat shield and the number of tiles needed for construction of this heat shield. Now, my results found that the 4.2 centimeter thick tile was the optimum thickness, and this had an average inside surface temperature of 150.8 degrees Celsius at the end time of the simulation, and it would have a total mass of 173.85 kilograms. It would need 361 tiles for construction. Now, to reflect on these results, all of these are within realistic ranges based on the values that I came across in my research, and it's important to optimize the mass of the heat shield because this means that you can increase the load carrying capacity of the space capsule and you have more room to deal with for more important calculations to do with trajectory and stuff like that. I do think there were some limitations due to the FlexPDE simulation because there was some nonlinear behavior in how increasing the thickness changed the final average surface temperature. And also in a real situation, the tiles would not be square. They would more likely be each a unique shape. And lastly, the scripting took some debugging, but this gave me practice with Python. Thank you for watching.